Wonderful. So hello everyone and welcome to this week's meeting of the ECHT Research Seminar. Today we're happy to have Angélica tell us about equivariant operads, multiplicative structures, and transfer systems.
Well, thank you, Jack, for the invitation, and thank you all for being here. I do see that at least one of you was in Belfast, and so this talk will be very similar to the talk that I gave in Belfast. So I shouldn't apologize, but like if you were in Belfast, you'll see a very similar talk than what I gave over there. So I'm going to tell you about sort of like some work in progress as part of my project of the MRC, the Mathematical Research Community that we met last summer doing projects on homotopical combinatorics. So for those of you who have been attending the ECHT summer reading on homotopical combinatorics, hopefully this will give you more context of like the some of the things that people have been working on. There's this is joint work with many people. So as the talk progresses, I'll mention various teams of people that have been working on these various things. And let me make sure that my slides are showing up. This is a story of trying to do things up to homotopy. And I mean, we're all homotopy theorists here, so we all know that like when you say up to homotopy, you need to be precise about what you mean. And I really wanted to start just like very basic, sort of like thinking, okay, if I have some operations up to homotopy, I have like first I have the strict version, and then when I go to homotopy, I have choices. And I really I want this partly to be a story about like the choices that I have when I go up to homotopy. So if I start with an associative algebra and I try to make that up to homotopy, well, we usually think of A infinity, which means up to all higher homotopies. But sometimes you don't have that, and you may stop at A1 or A2 and so on. And those are just things where like you have some homotopies, but you don't have all, right? And that's what the various ANs mean. And of course, like one actually should make this precise, and maybe like you use associahedra, or maybe you use specific operads in order to encode that. And if you go to commutative, same story, right? There's the infinity, which maybe is what we would like, but sometimes you don't have that. Sometimes you have E2, E3, and again, the idea is that sometimes you have commutativity up to some homotopies, but not all. And you may be seeing this E1 missing here, and maybe it's important to remember that E1 is the same thing as A infinity. And so what I want to tell you today is about what happens when I have G commutative and I want to make that up to homotopy. And again, trying to talk about the different choices that one has when that happens. For the purposes of this talk, G will be a finite group. I actually really wanted to start just like with what is G commutative on the nose, because I think sometimes we forget to think about all the different pieces that we have in the strict version, and then how those may become into play when I go to the up to homotopy world. So if I have a G space, meaning just a space with a G action, for every subgroup, I can look at the set of fixed points, and this is all the points in X that are fixed by every element in H. And when I have this collection of fixed points, I always have some natural maps. So I have an inclusion of H fixed points into K fixed points whenever K is a subgroup of H. And this is an exercise that you can give your undergrads, that like if you're fixed by everything in H, then they are particular fixed by everything in K. So this is an inclusion. And then there's actually a homeomorphism given by the G action from the fixed points with respect to H to the fixed points with respect to the conjugate subgroup. So these always exist if you have a G space. But then if you have a G commutative structure, meaning what? Meaning I could mean two things, but the two things mean the same thing. So X is a G space, and then I can have a commutative monoid structure that is compatible with the G maps, or you can think about it as you have a monoid with G maps with a G action given by monoid maps. The two things mean the same thing. When I'm in that setting, I have wrong weight maps, meaning that if I have K as a group of H, I have a map from the fixed points with respect to K to the fixed points with respect to H. And I really like seeing this example because it tells you where the commutativity comes in. So to give you the example of the map from X to the fixed points with respect to G, I can just take the map that sends X to the sum over the orbit. And it turns out that this element is a fixed point, and you do the computation. And again, this is one of those computations that you can give your undergrads. But very importantly so, the reason you have a fixed point is because the multiplication is commutative, or like the operation is commutative. And the operation, if the operation is not commutative, you do not have that this is a fixed point necessarily, because you have to reorder the summands in this. So the thing that I really want to emphasize here is that the presence of the wrong-way maps really relies on the commutativity of the operations. And if my operations were not commutative, I wouldn't have those wrong-way maps. So when you go to up to homotopy, since things are only going to be up to homotopy, you wouldn't necessarily have a map like this. And so it makes sense that maybe sometimes you'll have those maps and maybe sometimes you won't. So when I go to commutative up to homotopy, let me see if I can move it as well. Make this a little bit smaller. I need to make sure that I start putting constraints on what I mean by G commutative up to homotopy. And the first thing that I'm going to say is that I want to have a G space that has an underlying infinity structure. So for the purposes of this talk, I'm not going to talk about what happens when the underlying structure is less than E infinity. And there are people who are working in these questions when you don't necessarily have the full E infinity structure. And the thing that I really want to emphasize here is that even in the case that you have an underlying infinity structure, you can be in the situation in which you have no transfers whatsoever, or in the situation in which you have all transfers. And you can have things in between. And that's really kind of like what's driving the kinds of structures that you have here. And so here's an observation, which is that the existence of some transfers forces the existence of others. And there's a very simple case of that. So if you have three nested subgroups, L subgroup of K, L subgroup of H, well, if you have this transfer and you have this transfer, then you can compose them and you're going to have the big transfer. So there's going to be some compatibility between the transfers that you're going to have. So one way in which we can make this precise is by the theory of n infinity operads, which was developed by Blumberg and Hill, probably like since like 2015 or something like that. And I'm just going to jump in and give you the definition of what an n infinity operad is. So we're in the world of G spaces, although really you could do this in any homotopical setting where you have a G action. And an n infinity operad is an operad in that setting where the sigma in action is free. And for every n, and I should explain a little bit here, since my operads live in G top, each O of n has both a G and a sigma in action, and they commute. So I can really think about having a G cross sigma in action. And what we're going to say is that for every n and every subgroup of G cross sigma n, the fixed points with respect to the subgroup are either empty or contracted. So that's the one important condition. And then I'm going to have another condition, which is that the G fixed points are always non-empty. So I always have at least one operation that is fixed by the G action. And if I have a map of n infinity operads, I'm going to say that it's a weak equivalence precisely when the subgroups witness that weak equivalence, meaning I have weak equivalence for every collection of subgroups. And you can see that because of this condition over here, this is basically going to be, or they're either both empty or they're both contractible at the same time. So a few remarks about this definition. The first one is that this conditions implies that we do have an underlying infinity operad when we forget about the G action. And this is because we have this contractibility even when we have the trivial subgroup. And this is basically the definition of any infinity operad. And then moreover, the gamma fixed points are precisely encoding transfer maps, or among other things, they encode transfer maps. And I wanted to be very explicit about what I mean by that. So if you have a K as a subgroup of H, and you look at the index of K in H, you can take a subgroup of G cross sigma n. I'm going to call it gamma of H mod K, which I can construct as follows. So H mod K is an H set. So I can think about it as, well, maybe I order the elements, and then I can think about the permutation representation that is encoding this H set. So this set has an H action. If I label the elements with the numbers 1 through n, then I can think of my H action as a group homomorphism from H to sigma n. And if I think about the graph of that, this is a subgroup of G cross sigma n. So if I take an O algebra, that means that I have a G cross sigma n map from O of n to the mapping space from Xn to X. And what I mean here is all maps from Xn to X with the G action given by conjugation. And this is precisely how you encode an O algebra structure. You have these maps for each n, and they're compatible with the operads structure. And this has to be a G cross sigma n map, which means that this descends to a map of fixed points. And moreover, and this is something you can do very explicitly, there's a pretty natural map, or I mean, maybe natural is not the right word, because I need to use the fact that gamma here is constructed in this very specific way, which means that I chose an order for the H set H mod K. But you can construct a map from the fixed points of the mapping space to the mapping space from X K to XH. And so this actually tells you that if this is non-empty, your O algebra structure is giving you a transfer map like the one that you want. So the which fixed points you have tells you which transfer maps you're going to have, and this is part of what we should be thinking, that in an infinity operad, it has like this underlying infinity structure, and in addition, there's some transfer maps that are being encoded by the operad itself. Now I'm going to make this a little bit smaller. So I'm going to do a little bit of a jump here, and I'm going to tell you about transfer systems canons in the vacuum, and then I'm going to go back and connect them to the n infinity operads. So here I have my group G, and I'm going to have sub G just denote the lattice of subgroups of G. So I have all my subgroups, and they're ordered by inclusion. So I'm just going to be thinking about that. Usually what I'm going to do is I'm going to draw the Hasse diagram of this lattice of subgroups. And a transfer system on G is going to be a relation on the set of subgroups that satisfies a few conditions. The first one is that it is a partial order, meaning that it is reflexive and transitive in particular. It refines the usual inclusion of subgroups. And what that really means is that I can only have my relation if I have the subgroup relation. It is close under conjugation, meaning that if K is related to H in my transfer system, then the conjugate with respect to G of K is related to the conjugate with respect to G of H. And then it has this condition of being close under restriction. So if K is related to H in my transfer system, and I take a subgroup of H, then when I take the intersection of K and L, then I have the relationship between K intersect L and L. And this is just sort of like a close under pullbacks kind of restriction in the transfer system that I'm looking at. So these are the conditions on a transfer system. And I'm going to denote by TRG the collection of all transfer systems. And because these are relations, I can think about it as a poset on the refinement. Now, before moving on, I really want to emphasize that this is very combinatorial. And the reason I've gotten I got into thinking about transfer systems was because Kyle Ormbsy and I were looking for projects to work with undergraduates at Reed College related to homotopy theory. And we had a conversation with Jonathan Rubin, and this was like, oh, this is great. We can actually have undergraduates work on this. So I really want to emphasize that this is very combinatorial, and you can have undergraduates start playing around with this, just like coming up with examples and things like that pretty quickly without necessarily understanding the homotopy theory behind it. So to give you an example, if my group is CP, then the lattice of subgroups is pretty simple. It only has the trivial subgroup and all of CP. And then you look at the conditions on transfer systems and you realize that you have two of them. You have the one where you only have the identities, and you have the complete one where you have all of the pieces. And those are all of your transfer systems. And you should be thinking about this as, oh, well, this has no interesting transfers, and this has all the transfers. But moving up a little bit in difficulty. So if I look at CP, well, this should be CP squared, not CP sub 2. The subgroup lattice is a tower that has E, CP, and CP squared. And you start looking at the conditions and you realize that there's only two interesting conditions. There's a transitivity that tells you that if you have the two short transfers, then you must have the long one. And the restriction one, it's only interesting when it says that if you have the long one, then you must have the short. So you get these two conditions, and then you sit down for a few minutes and you come up with this being your lattice of transfer systems, meaning there's exactly 5 of them. At the bottom, you have the trivial one. At the top, you have the complete one, and then you have 3 other ones. And you start looking at the 2 conditions that I mentioned, and then you realize that this are the only things that you can have. So there's this beautiful theorem of Balchin, Bars, and Roitzheim, which says that the number of transfer systems for CP to the n is precisely the n plus first Catalan number. And if you've ever taught a combinatorics class, then you get really excited when you see that. And then moreover, the actual structure of the poset of transfer systems is what combinatorialists call the Tamari lattice, but maybe homotopy theories know better as the edges of the isociahedron. So if you take the isociahedron and you look at just the edges, and you'll actually put some directions to the edges based on like how you're moving your parentheses, it turns out that you get precisely the same structure. So then this is really exciting. This is combinatorialists really understand the Tamari lattice. So getting that the poset of transfer systems is a Tamari lattice is very exciting. So now for the connection between transfer systems and an infinity operads, first there's maybe you're already intuiting because I was talking about transfers and now I'm talking about transfer systems. The first piece is that if you give me an infinity operad, I can define a relation that I'm going to call a little arrow O by saying that K is related to H if and only if K is a subgroup of H. And when I look at the operad and look at the fixed points with respect to this graph subgroup that I defined before, if that is not empty. So I'm precisely going to encode which transfers are being seen by my operad. And it turns out that that is a transfer system. And maybe you shouldn't be surprised. The conditions on the transfer system were built precisely so that they would be encoding the things that the operad is seeing. And then more interestingly, so there's a theorem that is partly by Blumberg-Hill, and then there's independent work of Bonventre Pereira, Gutierrez White, and Rubin that shows that if I take the functor, so I have the category of n infinity operads, and I have the poset of transfer systems, which I can think of as a category because it's a poset. And so the map from O to the transfer system given by O turns out to be a functor, and because this is a poset, it's only meaning that like you have the right inclusions. So the statement of the theorem is that this induces an equivalence between the homotopy category of an infinity operads and the poset of transfer systems. And since this is a poset, this is saying a few things. First of all, it's saying that these mapping spaces are either contractible or empty. But more importantly, that the equivalence is saying that every transfer system can be realized from an infinity operand. And this is really the independent work from these three different teams was precisely proving that the essential surjectiveness, meaning that really every transfer system is realized. And here it's important for me to point out that the methods of the three papers are very, very different. And Rubin's method is a very explicit construction. This one is more like a model category kind of proof, and this one is like an explicit construction too. But it's thinking about operads as being operads in G sets being indexed by G trees rather than just being indexed by natural numbers. So the three constructions are very different. So if you give me an infinity operad, I can take an algebra in G spaces and I look at its sort of coefficient system of pi naught. And what I get is what Blumberg and Hill call an incomplete Tambara functor. And what's really happening here is that, so when you talk about an incomplete Mackey functor, when you have a Mackey functor, you have all these maps that are going the wrong way, meaning you have transfer maps. And when you have an n-infinity operad, well, you shouldn't expect to have all the backward maps, only the ones that are being encoded by your n-infinity operad. So you can actually make that precise by defining this incomplete Mackey functor, where you have all the maps in the right direction, but only the maps in the wrong direction that are being encoded by your transfer system or your n-infinity operad. And when you look at instead an O algebra in genuine G spectra, so because you're in genuine G spectra, your underlying additive piece is a complete, it has all the transfers because it's given by a genuine E infinity operad, and I should have said this before. A genuine E infinity operad is an example of an N infinity operad where all the transfers are there. So additively, this has all the transfers, but multiplicatively, it only has some of the norms. So when you look at the pi naught of x, you get what Blumberg and Hill call an incomplete Tambara functor, meaning that you're going to have all of the transfers, but you only have some of the norms. And Blumberg and Hill go ahead and define what it's called by incomplete Tambara functor, which is kind of like a Tambara functor, but you have only some of the transfers and some of the norms. And if you've ever done any computations with Tambara functors, you know that the existence of some norms implies the existence of certain transfers, because some of the formulas that you're going to write down for norms are going to involve writing certain transfers. So you're not going to be able to just have any random collection of norms and any random collection of transfers. You're going to have some compatibility between the norms that you see and the transfers that you see. So what Blumberg and Hill did is they figure out these conditions, and then David Chen translated it to the language of transfer systems. So the statement is that if you give me two transfer systems, this pair encodes the norm transfers of a incomplete Tambara functor if and only if this two conditions, which again are very combinatorial. One is that the multiplicative transfers are always contained within the additive transfers, and the other one is a kind of restriction kind of condition that says that if you have a square like this, so you have H and then two subgroups, L and K, and then you take the intersection of both. If the vertical arrows are in the multiplicative transfer system that you have, and this horizontal arrow is in the additive one, then the top one has to be in the additive one. And this is one of those conditions that it takes a while to wrap your head around it, but it's very combinatorial in nature. In terms of indexing systems, and now I realize that when I prepared the slides, it was in Belfast after like Mike Hill had given 3 talks about this stuff. So there's a little bit of a jump that I'm making here, and let me just explain briefly. Transfer systems are a way of encoding which transfers you see, and there's a separate way that is equivalent, which is called indexing systems, where what you're looking at is a collection of H sets for every H a subgroup of G. And in the language of indexing systems, this condition looks a little bit more generally as saying that if the H set H mod K is in the multiplicative piece, and you have some X, which is a K set in the additive piece, then you must have that the co-induce H set, which is the maps from H to K, so the K maps from H to X, that must be in the additive piece. No matter what, you should really be thinking about this as conditions that say, if you have something in the multiplicative piece and something in the additive piece, then something else must be in the additive piece. And if you have a transfer system that satisfies this condition, we're going to call it a compatible pair. In some joint work with Kristen Mazur, Constanze Roitzheim, Rekha Santhanam, Danika Van Niel, and Valentina Zapata Castro, we study the compatible pairs for the subgroups of the form CP to the RQ to the S. And I should say that this follows work of Mike Hill with a bunch of undergrads, where they fully find the combinatorics of the compatible pairs for CP to the N, kind of following the work from the Catalan numbers. They can do a full count of those. But here, it turns out it's really hard to count transfer systems on this. These are rectangular grids when you draw the lattice of subgroups. But it turns out that instead we have a theorem that talks about when a multiplicative transfer system has a unique additive piece. But this is not the work that I'm going to tell you about today. Instead, I'm going to tell you about realizing compatible pairs. So this is joint work with David Chan, Myungsin Cho, David Mehrle, Pablo Sanchez Ocal, Ben Szczesny, and Paula Verdugo, and this is part of our work of the mathematical research community that met last summer in upstate New York. And the question that we were trying to answer was the following. So when Blumberg and Hill talk about compatible pairs, they're working completely algebraically. They're just working with buying complete Tambara functors. They're not really having the operads play any role. They're just thinking algebraically, kind of like sort of like thinking, okay, when I have a Tambara functor, which norms imply which transfers, and that's how they got their definition. So our question was, is there an operatic interpretation of their result? And we tried to answer this question using the idea of operad pairs following definitions from Peter May, which were developed precisely when he was trying to talk about what it means to have an operad that is giving you some additive structure and an operad that is giving you a multiplicative structure. So I'm just going to jump ahead and give you the definition. So if you have two operads in some symmetric monadial category, I'm going to define an action of P on Q as a collection of maps. And I want you to see this and see how it's different than when we think about a module of operads. So here I have PQ, and then I have, PK, and then I have QJ1 through QJK. And then the map is going to send this not to the sum of the j's, but the product of the j's. And the idea here is that these maps are going to allow me to talk about sort of like the Q is giving me an additive operation and P is giving me a multiplicative operation that distributes over the additive operation, and the maps precisely allow me to talk about that distributivity. So this is why you have those. And so a rough version of a theorem of Peter May is that if P acts on Q, you can make sense of P algebras in the land of Q algebras. As I was saying, in the sense that Q is giving you an additive structure and P is giving a multiplicative structure that distributes. And so this operand pairs allow you to build that. So with that in mind, I can rephrase my question and actually split it up into two questions. So the first version is, if you give me two n-infinity operads, and I know that P acts over Q, is it true that then the pairs of transfer systems form a compatible pair? So that's the first question. And then the second question is the more interesting one, which is that if you give me a pair of G transfer systems that are compatible, can I actually build operads that realize that pair and such that P acts on Q? And this is the piece about realizing that pair. And if you look at this question, you realize that this is a very hard question because it talks about actually building operads with a certain collection of transfers. So somehow we need to look at the very, very hard proof of the theorem of Blumberg-Hill, Gutierrez-Pereira, and so on, right? And see if we can actually take those operads that realize compatible pairs, and in addition, build this operad action, which is a map of operads, which is not easy to build. So this is a deep and interesting and hard question to try to approach. But the first question is doable, and this one we did complete the work for this one during our week in New York. So this is a theorem. I'm not gonna read all the names again. So we did prove that if you give me two n-infinity operads and we know that we have an action, then the corresponding pair of transfer systems is indeed a compatible pair. Now, I want to give you an idea for the proof. Although, I mean, this is one of those proofs that it just revolves into making sure that you're very, very clear with notation, and you just need to follow everything very carefully, because what we need to prove is that if H mod K is in P, and we have some K set X in Q, then the co-induced thing is in Q. That's what we're supposed to do. And so we need to start taking representatives. So what's going to happen is that we're going to take the n being the index of K in H, and M is going to be the cardinality of X. And then what we know, because of these conditions, is that this is non-empty. These fixed points are non-empty, and these fixed points are non-empty. And what do I mean by this over here? Well, because X is a K set, I can still, maybe by numbering the elements, labeling the elements in X, there's going to be a graph subgroup of G cross sigma M that is going to basically be representing X, and that's what I'm going to call this. So I know that these two things are non-empty. That's the condition on that is being encoded here. And so I need to find some element that lives in some Q of something. It actually needs to live in Q of M to the N. And my operad pairing is built precisely to do that. So I take my A here. And for this one, for this B, I'm actually not going to take B everywhere. What I'm going to do is I'm going to take B multiplied by choice of coset representatives for the H mod K. And you follow your nose and you realize that this lands in the right fixed points in here. So you know that this is true because the fixed points with respect to this thing are going to be non-empty. So it's not very deep, but it involves just careful following through of all the definitions. Now, in order to answer the second question, we need to build an operad pair. And it turns out that if you look around, there's not that many operad pairs because these actions are really hard to construct. But there's sort of like a canonical operad pair that people have been working with for a long, long time, which is linear isometries and the Steiner operad. And if you read EKMA, you know that those two appear there, and it's precisely because you sort of like you use the linear isometries to talk about the multiplicative structure, and you use the Steiner operad to talk about the additive structure when you're talking about spectra. So just briefly, the linear isometries operad at level n is looking at linear isometric embeddings from n copies of R infinity to R infinity. And the operad structure is given by appropriately composing things. And then on the other hand, you have the Steiner operad. And in the Steiner operad, you're doing something really funny, but you should be thinking of the Steiner operad as sort of like a homotopical thickening of little disks. So in little disks, what you're trying to do is you're trying to embed a disk into another disk, and you have a collection of those such that the images are all disjoint. Well, in the Steiner operad, instead what you have is paths of embeddings. So you're looking at n distinct paths of embeddings, and with a condition, which is that at one of the endpoints of the path, you have the identity, and at the other endpoint, meaning at 0, the images are disjoint. So you should really be thinking that at this point, I basically have a version of the little disk operad, and then at this end, you just have the identity. And here we just kind of like have a picture as your path time goes on, you initially have these embeddings that are disjoint, and then as time goes on, at some point they're not going to be disjoint anymore because in the end they have to be the identity. And it turns out, and this is a theorem of Steiner, which actually sort of like came up with the Steiner operad partly so that there could be this action. There's an action of L and K, and I can tell you very briefly what the action is. So, so this F here, remember, is a linear isometric embedding from R infinity to the n into R, and these HIs are actually tuples of these paths of embeddings. So, what this operation does is that at time t and at this coordinate. So what do I mean by that? So notice that here, I'm supposed to give you J1 through Jn tuple of paths of embeddings. But in order to label a tuple here, I'm going to use the fact that there's an isomorphism of sets between taking the set of elements from 1 through J1 times J2 times Jn with the product of these sets. So I'm just going to order lexicographically, and I'm going to label by alpha 1 through alpha n my tuple here. What I'm going to do is I'm going to take the inverse of F, then I'm going to take the direct sum of the HI labeled by alpha I, and then I'm going to do F. And this, you're careful about it and you realize that it does give you an operad pairing. You can do this even equivariantly. There are equivariant versions of linear isometries and Steiner operads that are just built by replacing are infinity with any universe, G universe that you might have. And it turns out that you can actually get realizability for this pairs of compatible transfer systems. So what do I mean by that? So if you give me this universe, you have your LU and your KU, and this works even equivariantly. So you're going to get some, and I should say, if U is not necessarily a complete universe, but a universe where you have infinitely many copies of the representation, the finite dimensional representations that you see, those are all going to be examples of n infinity operads. So you're going to get realizability of some compatible pairs this way. But I probably should have said this before. It turns out that even with the same universe, linear isometries and the Steiner operad, they encode different transfer systems. And so you're only going to get those transfer systems that are given by linear isometries on one hand and Steiner operad on the other, but you're not going to get all possible pairs of transfer systems. There are many transfer systems that are neither given by something coming from linear isometries or something coming from Steiner. So to end the talk, I'm going to tell you about our current plan, which involves the following construction. So we're going to start with some operated set such that sigma n acts freely on it. And then I can do the following. I can take the mappings, this is just a mapping set, so all functions from G into O. And it turns out that this gives me an operad in G set. So here I'm doing something that is very silly. I'm basically building a G action just by looking at all maps from G into O. And then I'm going to do a construction that takes me from set into, well, simplicial sets initially, but eventually into topological spaces, which builds a set that is always contractible. And the way that I'm going to do it is I take my set and I go to the simplicial set that is given by x to the n plus 1. Notice that I'm doing x to the n plus 1 and not x to the n. And that n plus 1 is giving me an extra degeneracy that is what's going to force this to be contractible. For those of you who are more categorically minded, and you may have heard me say something like this before, what you can do is you take your set and you can construct a category that has exactly one morphism between any two objects. Peter May would call this a chaotic category. Some people don't like that name. And then you take the nerve, and then you take the classifying space, and this is the same construction that I described here. Now, what is the beauty of this thing is that if you, for example, had your sigma in action that was free, you still have a free sigma in action here, and you still have a free sigma in action here. So all throughout, you end up with an operad in G spaces. And it turns out that when you do this, you do get a genuine G infinity operad, meaning an infinity operad that has all the transfers. So this construction that seems very, very simple, it does give you like kind of like the strongest kind of an infinity operad that you could have. And so you can actually do this just with the linear isometries and the Steiner operad. And there's something very interesting that's happening here. I'm taking linear isometries and Steiner that have very interesting geometry because they're built with very, very interesting geometry. And then I'm forgetting about the topology because I'm thinking about this as living in sets. And then I build this whole construction here, but it turns out that all of this is nicely functorial, which means that I get an action. So this is a way of building genuine E infinity operads that have the action that I want. And the reason I might want to do this is because maybe what I want to do is I want to take sub-operads of these that give me the correct transfers. And this is actually something that you cannot do with the the equivariant linear isometries where you take a universe, even if you take a complete universe, it turns out that there's no, for some transfer systems, you cannot build a sub-operad that has that transfer system. And the problem is that when, like, you might think, oh, well, what if I just take some things that have the right fixed points and I just take the sub-operad generated by that? Well, it turns out that once you close under being a sub-operad, you end up adding some transfers that you didn't want when you wanted a smaller transfer system. So, but it turns out that with this other construction, and this is a theorem of Ben Szczesny, is that you can, no matter what transfer system you give me, you can always find a sub-operad that has the right that has the right transfer system. And again, this is not easy at all, because it does really mean that you have to make sure that that closing under the sub-operad is not adding some fixed points that you didn't want with respect to other subgroups. And the way that Ben does this is actually, instead of like taking some generators for a sub-operad, instead he looks at a specific collection of elements that have the right fixed points, and then he proves that that collection is a sub-operad. And this change actually helps a lot with trying to prove this. So as a remark, this theorem of Ben actually gives another proof of the equivalence of n-infinity operads and transfer systems. It's another construction of how to go back. And so this is as far as we've gotten with our team. So since we have an action of LG on NK, if I take any transfer system, I'm going to get an action from LT on KG. And if you're looking at this, you realize that I'm not quite proving my initial goal, because all I'm being able to prove here is that if you give me any transfer system, I can build a pair with the complete one. So additive is complete and multiplicative is not complete. So this is as far as we've been able to get so far. But we have a hope. Where's my hope? My hope is that we're going to be able to build on this in order to prove that for any compatible pair, you do get an action of LTM in KTA. And the thing that's happening right now is that if you actually think about the way that operad pairs are constructed, we need to make sure that if I look at my map given by the action of LG on KG, that it restricts appropriately, that I land in the right place. And again, this is some hard combinatorics that we haven't quite been able to figure out. But that's all I had for you today. So thank you for your time.